Alright gang, here we go. So this is Chem 2, Unit 4, and we're talking about molarity. Alright, so far in this unit we've been talking all about aqueous reactions, and we talked about acids and bases and redox reactions. No matter what kind of aqueous reaction we're doing, we always need to think about how many moles of whatever it is that we're reacting. So in order to keep track of how many moles we have in whatever solution we're talking about, we have to think about the solution's concentration. All right, so the concentration is really defined as the quantity of solute in a solution. Okay, the quantity of the solute. Remember, the solute is the thing you're dissolving, and then the solvent is the thing that you have that you're dissolving it in. So it would be water would be the solvent. Okay. So we call this amount the concentration. All right. There's several different units for concentrations, and as we move throughout the year, we'll talk about more and more as we go. For now, we're just going to focus on this guy here, molarity. This is by far the most common concentration that chemists use. All right. Molarity. It's always with a capital M, never a lowercase m. Because lowercase m means molality, which is a different form of concentration. But anyway, so molarity, capital M, and it's defined as the moles of solute divided by the volume of the solution. Okay, volume of solution, and remember, it always has to be in liters. Okay, so moles over liters, moles per liter. Okay, really, so you can just think of it as this, moles per liter. All right. And so really we can use molarity as this conversion factor between moles and liters, because really it's just a ratio. All right, and we'll do some math here. Okay, so it says, what is the molarity of a solution that is made by dissolving 3.68 grams of sucrose, C12H22O11, in sufficient water to form 275 milliliters of solution? All right, so really we're just going to find the concentration. Remember, molarity is equal to moles over liters, so that means we need moles and we need liters. So we've got grams, so we need to convert our grams to liters. So we'll put I'm going to work it up here because down here we'll do another problem. So we do 3.68 grams of sucrose, so that'd be the C12H22O11, right? And so we set up our little box here, and we put grams. I'm just going to call it sucrose down here because I don't want to write out this whole thing, and we're going to moles of sucrose, right? And so for every 1 mole, we have a certain number of grams. Well, we need to find the molar mass of our compound here. So we got 12 carbons, 22 oxygens, and 22 hydrogens, and 11 oxygens. All right, and we're going to add those guys up. So 12 times, this guy's big one, right? 12.01 for our carbon, 22 times 1.01 for the hydrogen, and 11 times 16.00 for the oxygen. All right, put that all in our calculator. So 12 times 12.01 plus 22 times 1.01 plus 11 times 16, get 342.34. All right, so 342.34. And remember, that's the molar mass, so that's in grams per mole, right? So we'll put this over here as the 342.34, all right? So 4 right there, okay. Whoop. And then, so we take our 3.68 divided by that, 3.68 divided by 342.34, and we get, in our 3.68 grams of sucrose, we have 0.0107. We don't really want to round yet, so I'm just going to go out a couple numbers, 495 moles of sucrose. All right, so that's how many moles of sucrose we have. So remember, concentration is moles per liter, so we're going to take our moles, which is that 0.0107495 moles of sucrose, and we're going to divide that by the volume of our solution, or the liters, right? In liters. So we said they told us it's 275 milliliters, but to get to liters, remember, we divide by 1,000, so it'd be 0.275 liters. All right, so we divide that guy by 0.275, and we get, so this, now we're going to worry about our sig figs, so we round to 3 sig figs, so it'd be 0.0391 molar sucrose. Okay, or in scientific notation, it would be 3.91 times 10 to the minus second molar sucrose. All right, so That would be, let's see, would have to be that one, right? C. Nice. All right, here we go. Practice exercise 2 says calculate the molarity of a solution made by dissolving glucose, okay, in sufficient water to form exactly 100 milliliters of solution. All right, so go ahead and pause the video. Try this one on your own. It's very, very similar, right? So remember, our molarity is moles per liter. Okay, so that means we need moles, so it's 5.00 grams of C6H12O6. All right, now we'll have to find the molar mass of glucose, because that's awesome, right? Moles of we're just going to call it gluck. All right, and we're going to from grams of gluck. All right, so here we go. So the molar mass, we have 6 carbons, 12 hydrogens, and 6 oxygens. All right, so 6 times 12.01 plus 12 times 1.01 plus 6 times 16. All right, so we say 6 times 12.01 plus 12 times 1.01 plus 6 times 16, 180.18. All right, so we put that down there, 180.18. All right, so we get 5 divided by that value. We get 0.02775 moles of gluck. All right, okay, and then we need the molarity, so we'll take our moles divided by our liters, 0.02775 moles divided by our liters. Now remember, it has to be in liters, and they gave it, so it'd be 0.100 liters. So we'll divide that by 0.1. We get, I guess I didn't have to plug that in my calculator, did I? So we get 0.2736, right? Yeah, 0.278 molar glucose. Oh my goodness. All right, we'll fix that. .278 molar glucose. All right. Now we're going to go backwards. We're going to use our molarity to calculate grams of the solute. All right, we're going to skip practice exercise 1 because it's essentially what we already did. Okay, so it says how many grams in practice exercise 2? It says how many grams of sodium sulfate are there in 15 milliliters of 0.5 molar sodium sulfate? All right, so we need to find grams. Remember, so right here it tells us that we have 0.50 molar. So this is like the same thing as saying we have 0.50 moles of Na2SO4 for every 1 liter, right? So that's the same thing as that. So if we were going to find grams, well, first we have to find moles. Okay, so if we want to we need to get rid of this liters, right? So we're going to just take our volume right here and multiply it, because if we multiply by liters, this is on the bottom, then the liters will cancel, right? So we'll just multiply by our liters. So we can divide by 1,000, so it'd be 0.015 liters, right? So our liters cancel. And so therefore we have, so it'd be 0.5 times 0.015, and we get 0.00075 moles, okay, of our sodium sulfate. So that's how many moles of sodium sulfate we have. And so now all we have to do to find the grams is convert that to grams using our molar mass, right? So we have to find the molar mass. So we've got 2 sodiums and 1 sulfur and 4 oxygens. All right, so sodium, 22.99, so we have 2 times 22.99 plus 1 sulfur, and sulfur is 32.07. And then 4 oxygens, 4 times 16.00. All right, so it'd be 2 times 22.99 plus 32.07 plus 4 times 16, 142.05. 42.05. So then we just convert our 0.0075 moles of Na2SO4 to grams. So we put moles of Na2SO4 down here, and there's one of those, to grams of Na2SO4. We just found that it's 142.05. So we take our 0.0075 times our 142.05, and we get 1.07 grams of Na2SO4. So if we had a 0.5 molar solution and we extracted 15 milliliters of it, we knew that we really extracted 1.07 grams of sodium sulfate. All right. It says, the part B says, how many milliliters of 0.50 molar sodium sulfate are needed to provide 0.038 moles of this salt. All right, so this is kind of the same idea. I'm going to draw a line here to delineate what we're working on. So this is the same idea, only we don't have to find molar mass, so it's not nearly as bad. So anyway, so remember that 0.5 molar really just says that we're starting with 0.50 moles of Na2SO4 for every 1 liter. Okay. All right. So what we need to do is get to liters. So we need these liters on. We need to get the liters by themselves, right? So instead of doing it this way, right, what we want to do is we're going to start with our moles. So we start with moles, and we're going to convert our moles into liters. So we have 0.038 moles of Na2SO4. And then notice that if we set up our dimensional analysis here, we can use this molarity, we can flip it upside down. We can put 0.50 moles of Na2SO4 on the bottom, and look, now these units will cancel, right? And the ratio from that to liters is just 1, right? 1 liter, right? And then notice that it asks for milliliters, so we can go from liters to milliliters just by dividing or multiplying by 1,000. For every 1 liter, we get 1,000 milliliters, right? So then we take our 0.038 moles divided by 0.5 times 1,000, and we get 76. Okay, and that's all we want is 2 sig figs. Okay, so 76 milliliters. Yeah, so this is in essence saying, like, if we know we needed to provide, so we're doing some sort of reaction, we know we needed to provide 0.038 moles of sodium sulfate in order for our reaction to take place. And we had 0.5 molar solution, we could just get 76 milliliters out of this, measured out in graduated cylinder or volumetric pipette. Bob's your uncle, and you're ready to roll. All right, you do need to be able to make solutions. So there's 2 different kinds of solutions that we're going to talk about making. All right, in class we're going to go over these more in depth and actually practice making solutions. So if you're making a solution from a solid, this is the steps you're going to do. Okay, you have to figure out what the mass is that you need to figure out the moles, right? And then once you figured out how much mass you need, okay, then you weigh it out, and you're going to dump it into a volumetric flask. Remember, these guys are volumetric flasks right here. They're kind of round bottom, long, skinny neck. Okay, and then you're just going to add your solvent. 99 times out of 100 is just going to be distilled water, deionized water. All right, and you're going to add that up. What I do is I fill it up to, about here or so with the water, and then once you've got it filled up there, then you swirl until all your solid is dissolved. Then you fill it up till you get to the line. And so in the neck of your volumetric flask, if that's the neck, it'll have this laser etched line in there. Okay, somewhere, oh my goodness, somewhere above the neck, right? And you're going to fill that guy up until your meniscus of your solution is right. Why do you do that to me? Okay, until the meniscus solution is like that. All right, only it's not going to make a V shape. It's going to be all curvy. But anyway, so you're going to put the meniscus right on that line, and then what you do is you stopper the end of it either with parafilm, or if you're feeling brave, you can just use your thumb, all right, or a stopper, and then invert that 3 or 4 times, and then you're good to go. All right, so that's making a solution from a solid. The other way we make solution is making it from another solution. So the way we would do this is it's called dilution. And so you're going to start with something that's more concentrated, and then take a small amount of that, add it to your volumetric, and then add solvent, so you get something that's less concentrated after. So the idea is that the concentration is lower than it was before, but the number of moles that you use don't change. All right. So they've drawn, in this example here, they've drawn 25 milliliters of some 1 molar stock solution, and then they put it over here. Okay, and then they added water until you got back up to the flask. So instead of it being 1 molar stock solution here, now they've made a new solution that's 0.1 molar. Okay, and so this is your formula that you're going to use to do that math. Okay, it's a molarity of the concentrated times the volume of the concentrated equals the molarity of the dilute times the volume of the dilute. And you should recognize that if we take molarity times volume, right, molarity times volume, well, that's the same thing as saying moles per liter, and that's the molarity times our liters. Our liters cancel and you're just left with moles. So that's exactly what we said in the previous slide, is that this whole side, so we're talking about the moles of the concentrated, is going to be equal to the moles in the dilute. All right, so that's really what we're using there to help us out. All right. So molarity times the volume equals molarity times the volume. Just make sure that you keep the concentrated on one side, dilute on the other. Plug in what you need and then solve the algebra. It's not too hard, really. All right, so we'll do 1 or 2 of these. It should be pretty easy. All right, it says, what volume of 2.5 molar lead to nitrate solution contains 0.05 moles of lead? All right. Okay, so so it says, what volume of 2.5 molar solution contains 0.5 moles of lead? All right, so we need to find out the moles of lead. Why are they asking us to do this? Forget that. Let's do B here. Okay, this is the math that we're talking about. Like, forget A. Okay. All right, so how many milliliters of 5.0 molar potassium chromate solution must be diluted to prepare 250 milliliters of a 0.1 molar solution? All right, so this is the molarity of our concentrated, and we know that because it's 5.0, and the other concentration they give us is 0.1. So this is going to be our MC. This guy is going to be our MD, and we know we need this here. We're making 250 milliliters of this, so this would be our VC, right? And so how many milliliters? Well, this will be our VD down here, and so this would be our VC. So anyway, molarity times the concentrated equals molarity times the concentrated. So we'll take 5.0 molar times the volume of our concentrated, which is our unknown. That's what we're trying to solve for, right? How many milliliters of our concentrated unknown are known, and that's going to be equal to the molarity of the dilute, which is 0.10 molar, okay, times the volume of our unknown. And so really, it doesn't, as long as, if we keep this in milliliters, like, and we put this in milliliters, the math works itself out. So we can leave this in milliliters, or you can always just, if that confuses you, you can always just leave it in liters and then convert it to liters and then convert it back out of liters. No matter what you do, it's all going to work out in the same. So we just divide both sides by 5. So we say 0.1 times 250 and divide by 5, and we get 5.0 milliliters. So in order to make this new solution, we would take 5 milliliters of our concentrated solution and then dilute it to 250. All right. Part C is essentially the same idea. We're taking 10 milliliters of a 10 molar stock solution of sodium hydroxide and diluting it to 250, and we want to know the new concentration. So we're taking the molarity of our stock, which is 10.0 molar, and we're taking 10 milliliters of it, 10.0 milliliters. All right, and we're diluting it to 250. So we want to know what the new molarity of our diluted solution is, times 250 milliliters. So we're going to take 10 times 10 divided by 250, and so we get 100 divided by 250. It's 0.4. I guess I could have done that in my head. 0.400 molar is going to be our solution. Is the concentration. Mg, molarity diluted. Okay. All right. And that's it for our solution. So we'll do several, practice problems, and I'll teach you how to use some new glassware and stuff like that. Should be a great fun time. Anyway, let me know if you have any questions.